Ancient star cities hold secrets that defy our understanding of the universe. These are globular clusters, dense spherical islands, each holding hundreds of thousands of ancient stars, all bound together and orbiting galaxies like our own. By the end of this journey, you will know 25 strange discoveries that are actively rewriting the rules of astrophysics. We will explore how some of these clusters seem older than the cosmos itself and why their stars are chemical fingerprints of a violent past. What cosmic mystery most captures your imagination? The first discovery on our list is perhaps the most unsettling of all. It is a cosmic paradox that seems to defy logic. When astronomers began to carefully measure the ages of stars within globular clusters, they found something impossible. According to the best stellar evolution models available, some of these ancient star cities appeared to be older than the universe itself. Think about that for a moment. How can a structure exist before the cosmos that contains it? This was not a small discrepancy. Early calculations suggested some clusters could be up to 16 billion years old, while our universe, based on the expansion rate we measure, is only about 13.8 billion years old. This created a profound tension, a glaring conflict at the very heart of cosmology. So how did we arrive at this impossible number? The key lies in reading the life stories written in Starlight. Astronomers use a powerful tool called the Hertzsprung-Russell diagram. It is essentially a graph that plots a star's brightness against its color or temperature. For a cluster where all stars formed at roughly the same time from the same cloud of gas, this diagram becomes a cosmic clock. You look for the point where the most massive stars are running out of fuel and beginning to leave the main sequence, the stable, long-lived phase of a star's life. This is called the main sequence turn-off point. The brightness and color of stars at that turn-off point tell you directly how long the cluster has been shining. The fainter and redder that turn-off point is, the older the cluster must be. When this method was applied to the most pristine, ancient globular clusters, the age it returned was simply too big. This paradox forced a revolution in thinking. Scientists realized the clusters were not breaking the universe. Instead, they were exposing the limits of our models. The age calculation depends on our understanding of the complex physics inside stars, like the rates of nuclear fusion reactions and the initial mixture of elements like hydrogen and helium a star is born with. If our models were slightly off, the age estimates would be wrong. So today, this age paradox is seen not as a crisis, but as a priceless calibration tool. These impossibly old clusters are cosmic laboratories, forcing us to refine our knowledge of stellar physics. By adjusting factors like nuclear reaction rates or the assumed initial helium abundance in our models, we can make the cluster ages align with the age of the universe. In this way, the ancient clusters are not universe breakers. They are universe refiners, helping us tune the very equations that describe how stars live and die. This cosmic calibration leads us directly to the second strange discovery, one that shattered a century of astronomical belief. For decades, scientists viewed globular clusters as the simplest systems imaginable. The classic story said that in a single, furious burst of creation, hundreds of thousands of stars were born from a pristine cloud of primordial gas. These sibling stars, all the same age and chemical composition, would then live out their lives together, a perfect example of a simple stellar population. It was an elegant, tidy picture, but it was completely wrong. The truth emerged when astronomers pointed their most powerful spectrographs, instruments that dissect starlight into a chemical fingerprint, at individual stars within the same cluster. They expected to see identical signatures. Instead, they found a stunning diversity. While heavy elements like iron were consistent, as the old model predicted, the amounts of lighter elements like sodium, oxygen, and aluminum varied wildly from star to star. Some stars had lots of sodium and aluminum but very little oxygen. Others showed the opposite pattern. This was impossible if all the stars formed from the same well-mixed gas cloud at the same time. You cannot get different chemical recipes from the same batch of cosmic ingredients. The only explanation was that globular clusters are not simple at all. They are complex fossil records of multiple generations. Here is how astronomers now believe it happened. That first, tremendous burst of star formation created the cluster's initial population. Among those firstborn stars were behemoths, many times the mass of our Sun. These giants lived fast, burned hot, and died young in spectacular supernova explosions. But crucially, before they exploded, their intense nuclear furnaces cooked up new elements like sodium and aluminum in their cores while consuming oxygen. These newly forged elements, along with helium, were then expelled through fierce stellar winds, polluting the remaining gas in the cluster. When the next wave of star formation ignited, perhaps 100 million years later, these new stars were born from this chemically enriched polluted gas. They carry the distinct signature of that pollution: high sodium, high aluminum, low oxygen. We see them today as a second, distinct population living right alongside their older siblings. In some massive clusters, we even see evidence for 3 or more distinct generations. This discovery completely transformed our understanding. A globular cluster is not a static snapshot of a single moment in time. It is a dynamic, multi-generational city where the ashes of the first generation literally became the building blocks for the next. This turns each cluster from a simple stellar museum into a layered archaeological dig, with each generation of stars telling a different chapter of a long and complex history. The discovery of multiple stellar generations points to a violent, energetic past, a history that may have left a dark and powerful relic at the very center of these clusters. This brings us to the third strange discovery, or perhaps more accurately, the third great mystery: the hunt for the missing intermediate mass black holes. For years, astronomers have theorized that the dense hearts of the largest globular clusters could be the perfect nurseries for a specific cosmic predator, a black hole with a mass between 100 and 100,000 times that of our Sun. This is the elusive intermediate mass black hole, a crucial missing link in the cosmic family. We know of small black holes, the remnants of massive stars weighing up to a few dozen solar masses. And we know of the monstrous supermassive black holes, millions to billions of times the Sun's mass, that lurk in the centers of galaxies. But the middle ground has remained frustratingly empty. Globular clusters, with their deep gravitational wells and crowded stellar environments, seemed like the perfect place to find one. The evidence, however, has been tantalizingly indirect and hotly debated. Take the magnificent Omega Centauri, the largest globular cluster orbiting our Milky Way. Observations from the Hubble Space Telescope meticulously tracked the motions of stars swirling around its core. The stars were moving far too quickly, as if caught in the grip of an invisible, concentrated mass. The simplest explanation for that gravitational pull is a black hole weighing roughly 40,000 suns. A similar story comes from a cluster named G1, which orbits the neighboring Andromeda galaxy. There, too, stellar velocities suggest a dark central beast of about 20,000 solar masses. Yet these findings are not definitive proof. The rapid stellar motions could, in theory, be caused by a tight knot of smaller stellar remnants, neutron stars and stellar mass black holes packed together. Distinguishing between a single, heavy anchor and a swarm of lighter ones is an immense challenge from such a great distance. This is why a confirmed detection would be a monumental discovery. An intermediate mass black hole would be the Rosetta Stone for understanding how black holes grow. Did they form in the early universe from collapsing giant gas clouds, or are they the result of countless smaller black holes merging together over eons within these dense star cities? Finding one would bridge the gap in our understanding and could even explain the origin of the supermassive giants that power distant quasars. The detective work is now entering a new, thrilling phase with the dawn of gravitational wave astronomy. Observatories like LIGO and Virgo are listening to the ripples in spacetime caused by colliding black holes. If an intermediate mass black hole resides in a globular cluster, it should occasionally capture and tear apart a passing star or merge with a smaller black hole. Such a cataclysmic event would send a unique gravitational wave signature across the universe, a clear fingerprint we could finally detect. So the hunt continues, a cosmic search for a shadow that may hold the key to how the universe builds its most extreme objects. Deep within the ancient stellar cities, astronomers found stars that simply should not exist. They are called blue stragglers, and they are brilliant, hot blue rebels that break all the rules. In a community where every star is a senior citizen over 10 billion years old, these stars stand out like vibrant, energetic teenagers at a retirement home. According to our models of stellar evolution, massive, hot, blue stars burn through their fuel in just a few 100 million years. In a globular cluster, every single one of them should have died in spectacular supernova billions of years ago. Yet there they are, shining defiantly. How can an old cluster contain such seemingly young stars? The answer lies in the extreme, crowded environment of the cluster itself, which offers two dramatic paths to a cosmic second youth. The first is a scenario of sheer, violent chaos. In the densely packed core of a globular cluster, stars are not the distant, solitary points of light we see from Earth. They are neighbors in a tight cosmic metropolis where close encounters are common and gravitational interactions are constant. Occasionally, two stars can be flung toward each other on a collision course. When they meet, they do not simply bounce apart. They merge in a titanic, fiery embrace. This stellar collision creates a single, new, more massive star from the combined fuel of its progenitors. This new star is hotter, bluer, and more luminous than either of its parents were. It essentially resets its evolutionary clock, appearing young and vigorous in a population of ancient stars. The second mechanism is more intimate but no less dramatic. It involves cosmic vampirism. Many stars in clusters live in binary systems, two stars locked in a gravitational dance. If they are close enough and one star begins to swell into a red giant as it ages, its outer layers can become gravitationally vulnerable. Its smaller, denser companion can then begin to siphon that material away, pulling a stream of hydrogen fuel across the space between them. The vampire star gorges itself on this stolen fuel, increasing its mass and reigniting its nuclear furnace with fresh hydrogen. It becomes hotter, bluer, and more massive, rejuvenated by its companion substance. Meanwhile, the donor star is left as a stripped-down, helium-rich core, a spectral ghost of its former self. These blue stragglers are not just cosmic curiosities. They are direct evidence of the dynamic, often violent social lives of stars in these dense environments. By studying their brightness, their temperature, and their location within the cluster, astronomers can trace the history of interactions that shape the cluster's core. They serve as brilliant markers, pointing to the regions where stellar collisions were most frequent or where binary systems have been dynamically altered over the eons. In their defiant blue light, we read a story of chaos, theft, and rebirth written across billions of years. The blue stragglers are not the only stars in these clusters with dramatic life stories. Some stars do not get a second youth. Instead, they are violently evicted, flung out into the galactic void at speeds so great they can never return. These are the hypervelocity stars, cosmic runaways ejected from their ancient homes by the ultimate gravitational slingshot. The theoretical mechanism behind their escape is a breathtaking dance of celestial bodies, a three-body interaction of perfect precision and immense power. Imagine a binary star system, two stars orbiting each other, drifting too close to the suspected intermediate mass black hole at the cluster's heart. The immense gravity of the black hole can violently disrupt this binary pair. In a flash of gravitational chaos, one star is captured into a tight orbit around the black hole, while its companion is catapulted away at an astonishing velocity, often exceeding 1 million miles per hour. This is not a gentle nudge, it is a cannon shot with the black hole and the captured star acting as the cannon, and the ejected star as the projectile. At such speeds, the star does not just leave the cluster. It can achieve escape velocity from the entire Milky Way galaxy itself, destined to wander the intergalactic darkness alone forever. Astronomers have been hunting these stellar fugitives for years, scanning the skies for solitary stars moving with impossibly high velocities against the general flow of the galaxy's rotation. When they find one, they work backwards, tracing its path across the sky like a detective following a trail of clues. The goal is to rewind its motion millions of years to see where it came from. In several compelling cases, these backward trajectories point directly back to the heart of our galaxy's massive central bulge, where a supermassive black hole provides the necessary power. But other hypervelocity stars have paths that seem to originate from the galactic disk, and here, globular clusters become prime suspects. A massive cluster swinging through the disk could, through this same slingshot mechanism, launch one of its own stars on a one-way trip into the void. Each hypervelocity star discovered is therefore a piece of forensic evidence. Its speed and trajectory tell us about the extreme gravitational environment that created it. Finding one that clearly originated from a specific globular cluster would be a smoking gun, confirming not only the presence of a dense central mass in that cluster, likely a black hole, but also allowing us to measure the intensity of its gravitational kick. These runaway stars are more than just cosmic curiosities. They are direct probes of the most violent gravitational interactions in the universe, natural experiments that reveal the hidden power lurking within the dense cores of ancient star cities. The same gravitational forces that can fling a star into exile also work on a far grander, slower scale, sculpting the entire cluster itself into a ghostly stream across the sky. This is the phenomenon of tidal tails, and they are the visible signature of a cluster's slow death by galactic cannibalism. Every globular cluster orbiting our Milky Way is engaged in a perpetual tug of war. The cluster's own gravity struggles to hold its stars together, while the immense diffuse gravity of the entire galaxy relentlessly pulls them apart. As the cluster swings along its elongated orbit, the difference in the galactic pull between its near side and its far side creates a stretching force, a tidal force, much like the moon's pull on Earth's oceans. Over billions of years, this relentless tugging peels stars away, not violently but steadily. The stars that escape do so from the cluster's leading and trailing points, forming two long, faint rivers of stars that trace the cluster's orbital path. These are the tidal tails, celestial footprints marking where the cluster has been and forecasting where it is going. The most stunning example of this is a cluster known as Palomar 5. Through wide-field telescope surveys, astronomers have found that Palomar 5 is not just a compact ball of stars. It is the bright, dense knot at the heart of two enormous stellar streams that stretch across an incredible 20 degrees of the night sky. That is over 40 times the apparent width of the full moon. These tails contain far more stars than the cluster itself holds today, meaning Palomar 5 is more stream than cluster, a system in its final act of dissolution. Within a few 100 million more years, it will likely cease to exist as a recognizable cluster at all, its stars completely assimilated into the Milky Way's diffuse halo. This process is a form of galactic cannibalism, where the larger galaxy consumes its smaller satellites. But these tidal tails are far more than just a funeral shroud for dying clusters. They have become one of astronomy's most powerful tools for detective work, Because the stars in a tidal tail remain gravitationally connected, they move together and preserve a record of the cluster's original orbit. By mapping the precise shape and curvature of these streams, scientists can reconstruct the gravitational landscape of the Milky Way's halo with exquisite detail. Any kink, warp, or gap in a stellar stream is a clue. It could be the fingerprint of a past close encounter with another cluster or a dwarf galaxy, a cosmic collision that happened billions of years ago. Even more importantly, the streams act as sensitive probes for the invisible scaffolding of the universe, dark matter. The tidal tails feel the gravitational pull of all mass, both seen and unseen. If the distribution of dark matter in the galactic halo is smooth, the streams will be smooth. If, however, the dark matter is clumpy, containing many small, unseen subhalos, these dark matter lumps would gravitationally punch through the stellar streams, stirring them up and creating observable gaps and wrinkles. By studying the pristine nature of streams like those from Palomar 5, astronomers are placing tight constraints on the nature of dark matter itself. In this way, the slow, graceful disintegration of a globular cluster writes a luminous map in the sky, a map that charts both the visible history and the invisible architecture of our galactic home. But the ghostly streams of dissolving clusters are not the only invisible forces at work. Some globular clusters appear to be hiding a different kind of secret, one that radiates with the most powerful energy in the universe. When the Fermi Gamma Ray Space Telescope began its survey of the sky, it revealed a startling phenomenon. Certain clusters, most notably the dense and ancient Terzan 5, were glowing with an unexpected excess of high-energy gamma rays. This was a profound puzzle. Gamma rays are the signature of the most violent events in the cosmos, produced by matter heated to billions of degrees or particles accelerated to nearly the speed of light. What could possibly be generating such intense radiation from within these quiet, ancient star cities? The leading explanation points to a population of cosmic lighthouses spinning in the darkness. These are millisecond pulsars, the remains of massive stars that have collapsed into city-sized spheres of pure neutron matter. A millisecond pulsar is a neutron star that has been spun up to dizzying speeds, rotating hundreds of times per second by siphoning material from a companion star. As they spin, they blast out focused beams of radiation, including gamma rays, like a celestial lighthouse. In the incredibly dense core of a cluster like Terzan 5, hundreds or even thousands of these faint, rapidly spinning pulsars could exist, each too dim to detect individually from our distance. But their combined gamma ray output would create a diffuse, powerful glow exactly matching the Fermi telescope's observations. This would make these clusters the richest known repositories of these exotic stellar remnants in the entire galaxy. Yet there remains a more speculative and far more thrilling possibility. The same gamma-ray signal could, in theory, be the long-sought signature of dark matter annihilation. The hypothetical weakly interacting massive particles, or WIMP, that could make up dark matter are thought to be their own antimatter counterparts. If two of these particles were to collide within the dense gravitational well of a globular cluster, they would annihilate each other in a flash of energy, producing a spray of gamma rays. A cluster with the right density and the right amount of unseen mass could therefore be a natural particle physics laboratory, one where we might finally catch dark matter in the act. This dual possibility places clusters like Terzan 5 at the frontier of two great mysteries. They are either unparalleled stellar graveyards, teeming with more spinning neutron stars than we ever thought possible, or they are our first direct window into the invisible substance that shapes the cosmos. For now, the millisecond pulsar explanation is the most conservative and likely answer, but the dark matter hypothesis lingers, an irresistible whisper of a deeper truth. Every new observation of these gamma-ray bright clusters tightens the constraints, forcing the invisible, whether it is a swarm of dead stars or something far more exotic, to slowly reveal itself. The search for planets has always focused on the quiet suburbs of the galaxy, around solitary stars like our Sun. Yet the discovery of a world within the ancient, crowded cluster Messier 4 shattered that assumption entirely. This planet does not orbit a normal star. It exists in a system of stellar corpses, circling a millisecond pulsar and its white dwarf companion. To understand how bizarre this is, you must picture the environment. Globular clusters like M4 formed when the universe was young and metal-poor, meaning they lack the heavy elements like iron and silicon that are the fundamental building blocks of rocky planets. Furthermore, the stars are packed so densely that gravitational encounters are frequent, threatening to rip any fledgling planetary system apart. The very idea of a stable, orbiting world surviving here for over 10 billion years seems laughable. And yet, there it is. Its presence is inferred through the impeccable clockwork of the pulsar it orbits. The regular pulses of radio waves from the spinning neutron star show tiny, rhythmic variations, a telltale wobble caused by the gravitational tug of an unseen companion. The data reveals a planet with about 2.5 times the mass of Jupiter, locked in an orbit that takes about 100 Earth years to complete. Its existence forces a radical rethink. Perhaps this world did not form in a placid disk of gas and dust around a newborn star, the way we believe our solar system did. In the chaotic early days of the cluster, it might have been forged from the debris of a catastrophic event. Maybe the destruction of a star that ventured too close to the pulsar binary system, or the remnants of a stellar collision. This makes it a possible survivor of an almost unimaginably violent birth. Alternatively, it could be a second-generation planet, forming from a disk of material created when the white dwarf companion donated mass to spin up the pulsar. This single, strange world, orbiting a lighthouse of the dead, proves that planets are far more resilient and resourceful than we ever dreamed. It suggests that wherever there is material and gravity, in even the most hostile corners of the galaxy, the universe finds a way to build worlds. The planet orbiting a pulsar in Messier 4 is a testament to cosmic resilience, but to understand the very fabric of these clusters, we must look at the air the stars breathe. Discovery 9 reveals a strange elemental imbalance, a pervasive helium problem. When astronomers dissect the light from cluster stars, they find a puzzling signature. While the iron content is uniformly low, as expected for these ancient systems, some stars show a clear and significant overabundance of helium in their atmospheres. This is not a trivial detail. Helium is the second lightest element forged in the Big Bang and cooked in the cores of stars. Finding too much of it in certain stars is a direct clue to a polluted past. This helium excess is the smoking gun that directly connects to the mystery of multiple stellar generations. Recall that the first generation of massive stars, living fast and dying young, would have fused hydrogen into helium in their cores. As these giants approached the end of their lives, fierce stellar winds would have blown this newly minted helium out into the surrounding cluster gas, enriching it before the next wave of star formation began. The second generation of stars then formed from this helium-enriched material, literally building themselves from the ashes of their predecessors. So, a star with high helium is wearing a badge that says, "I am not from the founding population. I am a child of the aftermath," but the implications of this extra helium go far beyond simple chemical tagging. It fundamentally alters how a star lives its life. A star born with more helium in its core is more efficient at nuclear fusion. It burns hotter and brighter, and it has a different evolutionary path. For a given mass, a helium-rich star will appear bluer and more luminous than a helium-normal star. This single fact helps unravel several long-standing puzzles in cluster observations. Look at a color magnitude diagram of a globular cluster, that graph that plots a star's color against its brightness. Astronomers noticed that certain branches of the diagram, like the horizontal branch where older, evolved stars reside, were much broader and more spread out than models could explain with a single chemical recipe. Some stars on that branch were inexplicably blue. When they factored in variable helium abundances, the pieces clicked into place. The helium-rich second-generation stars, burning hotter, naturally occupied the bluer, brighter parts of these evolutionary sequences. This helium variation is the key that finally allowed the theoretical models to match the messy, beautiful reality of the observed starlight. It also subtly influences age estimates. A helium-rich star evolves faster than a standard one, meaning that what looks like a slightly younger star might just be a helium-enhanced one. So this pervasive helium, this legacy of the first stellar giants, does more than just mark a star's lineage. It rewrites the stellar life cycle, solves color puzzles, and reminds us that in these ancient cities, even the most basic ingredients tell a story of violent creation and rebirth. Helium paints a portrait of stellar ancestry, but some clusters hide a gravitational signature so immense it challenges their very identity. This is the overmassive black hole conundrum, perfectly illustrated by the mysterious cluster known as Messier 54. From our vantage point, M54 looks like a magnificent, if somewhat large, globular cluster orbiting the outskirts of our Milky Way, but appearances are deceptive. M54 is not truly a citizen of our galaxy. It is the captive heart of another. This cluster sits squarely at the center of the Sagittarius dwarf elliptical galaxy, a small satellite galaxy currently being torn apart and consumed by the Milky Way in a slow-motion act of galactic cannibalism. This crucial fact changes everything. When astronomers measured the motions of stars whipping around the core of M54, they found velocities that demanded a central dark mass of staggering proportions, a black hole potentially weighing in at several thousand solar masses. That is far heavier than any intermediate mass black hole predicted for a typical globular cluster. The sheer scale of this hidden object points to a different origin story entirely. In the standard hierarchy of the cosmos, globular clusters are star cities, but dwarf galaxies are nations with their own government, a central supermassive black hole. When a large galaxy like ours devours a smaller one, the process is messy. The outer stars of the dwarf galaxy are stripped away, forming great tidal streams. But the very core of that small galaxy, its dense nucleus and its central black hole, can survive intact for a very long time. This is what M54 appears to be, not a born globular cluster, but the stripped, naked nucleus of a devoured galaxy. It is a galactic ghost, a surviving heart beating inside the body of its consumer. This discovery blurs a fundamental line and ignites a heated debate. How many of the largest, most massive globular clusters in the Milky Way's halo are actually these imposter nuclei? The magnificent Omega Centauri, with its own suspected massive black hole, is a prime candidate. So too might be G1 in Andromeda. Each one is now a subject of intense scrutiny. The distinction is not merely academic. A true globular cluster forms from a collapsing cloud of gas within a larger galaxy. A stripped nucleus is the remnant of an independent galactic system that failed to survive. Their internal structures, their star formation histories, and the very nature of their central gravitational anchors could be profoundly different. By studying these overmassive objects, we are essentially performing cosmic archaeology, sifting through the wreckage of ancient galactic collisions to understand how galaxies like our own were built, piece by piece, from the cannibalized remains of their smaller neighbors. The question lingers when we look at the densest, oldest star clusters in our sky. Are we seeing cities, or are we seeing the tombstones of vanished galaxies? Our galaxy's collection of globular clusters presents a silent, aging population, a fact that leads to a profound and simple question: where are all the young ones? The Milky Way is home to over 150 of these ancient star cities, each one a relic over 10 billion years old. Yet, we have found no globular clusters being born in our galaxy today. This absence is a glaring gap in the stellar life cycle, a missing chapter in our own cosmic backyard. To see what we are missing, we need only look to our small, irregular neighbor, the Large Magellanic Cloud. There, nestled within the vast Tarantula Nebula, lies a spectacular stellar nursery called R136. It is a young massive cluster, a seething cauldron of newborn stars, some over 200 times the mass of our Sun, blasting out radiation and stellar winds. R136 is only 1 or 2 million years old, a cosmic infant, and in a few billion years, once its short-lived, brilliant giants have died off, it will likely settle down to become a mature, long-lived globular cluster, much like the ancient ones we see in the Milky Way. So why does the Large Magellanic Cloud have this vibrant nursery, while our larger, grander galaxy appears sterile? The answer lies in the recipe and the timing. To bake a globular cluster, you need a very specific set of ingredients and conditions. You require an enormous, dense, and massive cloud of molecular gas, cold and turbulent, on a scale dwarfing any nebula in our present-day galaxy. Then you need a trigger, a colossal shockwave from a nearby supernova or a galactic collision, to make that cloud collapse in on itself in a single, catastrophic burst of star formation, converting most of its gas into stars at once. This creates the dense, bound system we recognize. In the early universe, conditions were perfect for this recipe. The cosmos was smaller, richer in pristine gas, and far more chaotic. Galaxies collided and merged frequently, their gas clouds slamming together and igniting furious waves of star formation. It was a universe-wide era of intense cosmic construction, and globular clusters were one of its primary products. Our ancient clusters are the survivors from that violent, fertile epoch. Today, the Milky Way is a relatively quiet, mature spiral galaxy. Its remaining gas is more diffuse, spread thin in a vast disk. The giant, dense molecular clouds capable of forming a globular cluster in one go are exceedingly rare. When large star-forming regions do appear, like the Orion Nebula, they tend to produce open clusters, looser, less massive families of stars that will eventually drift apart. The galactic environment itself has changed. The sheer gravitational turbulence and frequent mergers that once provided the necessary shockwaves have largely subsided. Our galaxy's current star formation is a slower, more steady process, ill-suited to forging the dense, gravitationally bound islands of a globular cluster. So the clusters we see are not just old, they are living fossils, celestial dinosaurs from a bygone era when the universe built its structures in a more frantic, more colossal style. Their continued existence, orbiting quietly in our halo, is a permanent testament to the galaxy's wild and explosive youth. The distinction between a city and a nation seems clear until you find a metropolis that defies all categories. This is the identity crisis posed by Discovery 12, the revelation of ultra-compact dwarf galaxies. For decades, astronomers surveying the sky would occasionally spot a small, dense, fuzzy patch of light in galaxy clusters like Virgo or Fornax. They catalogued these objects as unusually large globular clusters, perhaps outliers at the extreme end of the size scale. But when powerful telescopes like Hubble finally measured their true properties, the numbers were staggering. These were not mere star cities, they were entire galactic cores in disguise. Take the object known as M60 UCD1, orbiting the giant elliptical galaxy M60. It is a sphere of stars only about 300 light-years across, incredibly dense, yet it contains a mind-boggling 140 million stars. That is nearly twice as many stars as our entire Milky Way has in its central 10,000 light-years, all packed into a volume 1,000 times smaller. But the real shock came when astronomers studied the motions of stars at its heart. They were orbiting so fast that the only explanation was a gravitational monster, a supermassive black hole with a mass of 21 million suns. That single black hole accounts for a phenomenal 15% of the entire dwarf galaxy's mass. This is not a feature of any globular cluster. It is the hallmark of a galactic nucleus. The conclusion is inescapable. Ultra-compact dwarfs are not born this way. They are the ravaged remnants of larger galaxies that ventured too close to a giant like M60. Over billions of years, the immense tidal forces of the larger galaxy stripped away the outer stars, a process of cosmic strip mining that left only the dense, nearly indestructible core behind. What we see today is the galactic equivalent of a chicken nugget, the processed, compacted heart of something that was once much larger and more complex. This discovery has irrevocably blurred the line between the largest star clusters and the smallest galaxies. It forces us to ask a profound question about our own galactic backyard. When we look at Omega Centauri or Messier 54 with their own suspiciously massive central objects, are we looking at true globular clusters, or are we, in fact, looking at the same type of stripped ultra-compact dwarf, a devoured galaxy core that just happens to be orbiting our Milky Way? The simple, two-category universe we once imagined, where objects are either clusters or galaxies, has collapsed. We now see a continuum, a spectrum of stellar systems where the most massive clusters and the smallest galaxies overlap, their identities forever intertwined by the violent history of galactic cannibalism. Omega Centauri's true nature is written in the chemical signatures of its stars, a record so chaotic it defies the very definition of a globular cluster. In a typical cluster, every star shares a nearly identical fingerprint of heavy elements, particularly iron. This uniformity is the hallmark of a single, rapid burst of star formation from a well-mixed cloud of gas. Omega Centauri shatters that expectation completely. When astronomers analyze its millions of stars, they find a staggering diversity. The iron content, what astronomers call metallicity, varies by a factor of 10 from star to star. Some stars are extremely metal-poor, almost pristine relics from the early universe. Others are significantly richer in iron, indicating they formed from gas already polluted by generations of supernova. This range is not a smooth gradient. It is broken into at least 4 and possibly more distinct stellar populations, each with its own specific blend of iron and other elements. Even more telling, these different chemical groups appear to have different ages, spanning a gap of up to 2 billion years. This is not the story of a single event. It is the complex, layered history of a system that kept forming stars over an extended epoch. Such a wide metallicity spread and prolonged star formation is utterly unheard of in a genuine globular cluster. It is, however, the classic signature of a dwarf galaxy. Small galaxies with their deeper gravitational wells can hold onto their gas for much longer. Multiple waves of star formation can occur, with each generation enriching the galactic gas with more iron from supernova, leading to the chemical diversity we observe. The compelling conclusion is that Omega Centauri is not a cluster at all. It is the surviving heart of a small galaxy that once orbited our Milky Way independently. Billions of years ago, as this dwarf galaxy swung too close, the Milky Way's immense tidal forces began to strip it apart. The process was a slow cosmic dissection. The outer stars and gas of the dwarf galaxy were peeled away, eventually dissolving into the Milky Way's halo to become part of its diffuse stellar stream. But the very core of that small galaxy, its densest and most tightly bound central region, resisted complete destruction. It survived as a self-gravitating island, a galactic fossil we now call Omega Centauri. This explains everything: the wide range of metallicities, the multiple ages, its enormous mass, and the suspected massive black hole at its center. It is a unique artifact, a trophy from an ancient act of galactic cannibalism, offering us a direct look at the building block from which our own galaxy was assembled. The chemical fingerprints within a cluster tell a story, but one pattern is so specific it reads like a forensic report. Across countless globular clusters, astronomers see a precise and powerful relationship between two elements, sodium and oxygen. As you measure star after star, you find a clear anti-correlation. When a star shows high levels of sodium in its atmosphere, it invariably shows low levels of oxygen. The more sodium, the less oxygen. This is not a random scatter of points. It is a tight, descending line on a graph, a fundamental signature that something systematic happened to the gas from which these stars formed. The first generation of stars born from pristine gas sits at one end of this line, high oxygen, low sodium. The later generations, polluted by the winds of those first stars, sit at the other, low oxygen, high sodium. But the plot thickens dramatically when you look at the finest data. This descending line is not perfectly straight. In many clusters, it shows a distinct and sudden bend, a sharp turn that astronomers call the knee. Imagine drawing a line that slopes downward steadily, and then, at a specific point, it kinks and continues downward at a steeper angle. That knee is a frozen moment in time, a chemical fossil of profound importance. It tells us that the pollution event was not a smooth, continuous process. It happened in distinct phases, with different sources turning on and off. The leading theory points directly to the lives of the most massive stars in that first generation. These giants do not pollute their surroundings all at once. Their winds blow in stages, each stage carrying a different chemical mix from a different layer of the star's interior. Early, weaker winds might carry material processed at relatively low temperatures, altering the sodium and oxygen ratios in one way. Then, as the star nears its death, more powerful winds rip from deeper layers where nuclear burning was more extreme, creating a different chemical signature. The knee in the data marks the transition between these two pollution events. It is the point where the first type of polluting wind stopped and the second, more extreme type began. When that second burst of enriched gas flooded the cluster, it mixed with what was left of the original gas and the material from the first winds, and then the next generation of stars froze that new mixture into their composition. By finding and measuring the precise location of this knee in different clusters, astrophysicists can effectively read the mass and the life story of the polluting stars that created it. It allows them to estimate how massive those first stars were and how quickly they lived and died. This tiny bend in a graph of elemental abundances is therefore a direct window into a brief, violent epoch over 10 billion years ago, a timestamp written in sodium and oxygen that captures the moment the first stellar giants began to die. Within the crowded stellar metropolis of a globular cluster's core, the quiet companionship of a binary star is a fragile thing. This environment is a perpetual demolition derby, a gravitational arena where close encounters are not rare events but a fundamental part of life. When a binary star system drifts through this dense neighborhood, its fate is decided by a chaotic gravitational dance. A passing star can interact with the binary in one of two dramatic ways. Sometimes the interloper steals energy from the binary's orbit, causing the two stars to spiral closer together in a process called hardening. Their embrace becomes tighter, faster, and more intense. In other encounters, the gravitational kick is so strong it completely severs the bond, flinging one star away into the cluster while leaving the other with a new, temporary partner. Over billions of years, this relentless churn creates a bizarre zoo of exotic stellar relationships that simply cannot form in the quiet galactic suburbs where our sun resides. One of the most spectacular results is the X-ray binary. Here, a hardened binary consists of a stellar corpse, a neutron star or a black hole, locked in a tight orbit with a living companion star. As they whirl around each other, the immense gravity of the dense corpse can strip material from the outer layers of its neighbor. This stolen gas doesn't fall directly in. It spirals down, forming a superheated disk of plasma around the neutron star or black hole. Friction within this accretion disk heats the material to millions of degrees, causing it to glow with intense X-rays, visible across the galaxy as a beacon of violent partnership. Then there are the millisecond pulsars, those cosmic lighthouses we encountered earlier. Their incredible spin is a direct product of this environment. Many begin as part of an X-ray binary where the neutron star is actively feeding. As matter streams onto its surface, it transfers not just gas but also angular momentum, effectively spinning the pulsar up faster and faster, like a child's top being whipped repeatedly until it rotates hundreds of times per second. When the donor star is finally exhausted, what remains is a rapidly spinning pulsar, its acceleration a permanent record of a long-ended feast. The core's graveyard holds quieter relics too, like detached binary white dwarfs. These are the Earth-sized embers of sun-like stars that have burned out. In the cluster's hectic core, such pairs can be brought together through dynamical interactions. They orbit each other silently, often so close that their orbital period is measured in mere minutes. These serene binaries are cosmic time bombs, however. As they circle, they lose energy by emitting gravitational waves, causing them to spiral inward ever so slowly. Billions of years from now, they will merge, potentially triggering a spectacular supernova explosion. So the dense heart of a globular cluster is far from a serene retirement home. It is a dynamic factory, a bustling hub where gravity constantly reshuffles stellar partnerships, forging the most extreme and energetic relationships in the galaxy. These exotic binaries are forged in the frantic core, but to understand where a cluster itself came from, you must look to its path through the void. The orbits of globular clusters tell a story of pure chaos. Unlike the Sun and most stars in the Milky Way's disk, which travel in neat, circular paths around the galactic center like cars on a racetrack, the clusters move to a different, wilder rhythm. They plunge around the galaxy on elongated, randomly inclined orbits, swooping in from great distances only to be slung back out again. This creates a vast spherical swarm known as the galactic halo, a three-dimensional cloud of ancient stars and clusters enveloping the flat disk. This stark difference in motion is a fundamental clue written in gravity. The orderly rotation of the disk stars points to a calm, settled origin. They formed from a gently collapsing, spinning cloud of gas that flattened into a disk, much like a spinning ball of pizza dough. The chaotic orbits of the halo clusters, however, scream of a violent external origin. They are not native to the Milky Way's main body. The leading theory is that most of these clusters were not born here at all. They are celestial trophies captured during the Milky Way's long and violent history of galactic cannibalism. Billions of years ago, our galaxy was surrounded by numerous small satellite galaxies, dwarfs much like the Magellanic Clouds we see today. Each of these dwarfs likely had its own family of globular clusters. When the Milky Way's immense gravity eventually captured and tore apart these smaller galaxies, the process was messy. The diffuse outer stars of the dwarf galaxy were stripped away, dissolving into streams, but the globular clusters, being incredibly dense and tightly bound, proved far more resilient. They survived the tidal forces essentially intact. As their parent galaxy was dismantled, these clusters were set free, but they did not inherit the Milky Way's orderly rotation. Instead, they kept the unique orbital energy and direction they had from their original galactic home. That inherited motion, a fossil of a long-dead dwarf galaxy, is what we see today as a random, plunging path through the halo. So every time a cluster like Messier 3 or Palomar 5 makes its long, slow dive toward the galactic center and swings back out, it is retracing the final, chaotic moments of its original parent system. Their orbits are not random. They are scars, permanent records of ancient collisions that helped build the galaxy we live in today. By mapping these wild paths, astronomers are performing celestial archaeology, reconstructing the sequence of mergers that assembled the Milky Way, one captured star cluster at a time. The wild orbits of captured clusters set the stage for a slow, internal rearrangement governed by a simple, relentless law of gravity. Within the crowded confines of a globular cluster, a silent sorting is always underway. This is the mystery of mass segregation, a gravitational phenomenon where the heaviest stars and stellar remnants gradually sink toward the cluster's core, while the lighter stars are pushed outward to the halo. Picture a giant jar filled with mixed nuts. If you shake the jar for a while, the larger, heavier Brazil nuts will eventually settle to the bottom, while the smaller peanuts rise to the top. A globular cluster does something remarkably similar, but instead of shaking, the mechanism is countless gentle gravitational nudges between stars over billions of years. Every time two stars pass near each other, they exchange a tiny amount of energy and momentum through their gravitational pull. On average, these encounters tend to transfer kinetic energy from the more massive objects to the lighter ones. The heavier star slows down a little, losing some of its orbital velocity, and thus sinks deeper into the cluster's gravitational well. The lighter star gains a bit of speed, moving into a wider, higher orbit. This process, called dynamical relaxation, is incredibly slow by human standards, but over the lifetime of the universe, it fundamentally reshapes the cluster's internal anatomy. The consequence is a starkly stratified stellar metropolis. The very center becomes dominated by a dense concentration of massive objects, neutron stars, black holes, and the most massive main sequence stars and giants. This central region grows ever denser, a simmering pot of gravitational interactions. Meanwhile, the outer regions become a diffuse cloud of lower mass stars, primarily red dwarfs and older, lighter stellar remnants that have been gravitationally evicted from the core. Observing this process in detail is like watching a dense stellar system slowly approach a state of thermodynamic equilibrium, a concept borrowed from physics where energy is evenly distributed. The cluster is essentially trying to settle into the most statistically likely arrangement of its stars, a configuration where no further net exchange of energy occurs. By measuring how far this segregation has progressed in clusters of different ages and densities, astronomers can clock the relaxation time, the timescale it takes for these gravitational encounters to thoroughly mix the stellar population. A young, loose cluster might show little segregation. An ancient, dense one like Omega Centauri shows a dramatic central concentration of heavy stars. This isn't just academic. Mass segregation has direct, observable consequences. It explains why the brilliant blue stragglers, which are relatively massive, are almost always found near the cluster centers. They sank there. It also predicts that the core will become a breeding ground for exotic binaries and collisions, as the densest population of objects is forced into close proximity. Furthermore, this process may solve a puzzle about the cluster's ultimate fate. As the heaviest objects, the stellar mass black holes, sink to the very center, they may interact, merge, and even form a single, growing intermediate mass black hole. Or they may eventually receive such a strong gravitational kick from an interaction that a whole swarm of them is ejected from the cluster entirely, leaving behind a lighter, puffier core. The silent sinking of the giants is therefore a key driver of the cluster's long-term evolution, a slow-motion choreography that writes the future of these ancient star cities in the language of gravity. The silent sorting of stellar masses over eons leads to a graveyard of stellar remnants, yet this graveyard holds a peculiar silence of its own. Despite the undeniable presence of thousands upon thousands of white dwarfs and neutron stars within globular clusters, the telltale signs of their violent births are conspicuously absent. We find no expanding shells of gas, no glowing nebulae like the crab that mark the site of a recent supernova. This is the mystery of the missing supernova. It is as if an entire city's population died of old age, leaving behind their bones, but with no record of the dramatic events that ended their lives. This absence is a profound clue, pointing to conditions in the early universe that were radically different from anything we see today. One compelling explanation is that the very first supernova in these clusters were cosmic overachievers. The earliest stars born from pristine hydrogen and helium, are thought to have been monstrously massive, many hundreds of times the weight of our Sun. When such a behemoth reaches the end of its life, it does not go quietly. It undergoes a pair instability supernova, a detonation of such staggering power that it completely obliterates the star, leaving behind no dense core, no neutron star or black hole. It is a total self-annihilation. The explosion would have been unimaginably energetic, a blast wave that would have scoured the cluster clean. It would have ejected every last wisp of remaining gas, the raw material for future star formation, out into intergalactic space. With no gas left to form new stars, the cluster's brief era of furious creation would have ended abruptly. And with no gas left for the supernova blast wave to slam into and light up, the remnant itself would have dissipated into the void almost instantly, leaving no lasting visible structure for us to find billions of years later. Another possibility is that some of these primordial giants skipped the explosive finale altogether. If a star is massive enough and has a particular chemical composition, its core collapse might be so complete that it forms a black hole directly, with a whimper instead of a bang. A faint, failed supernova, producing a minimal flash and little ejected material, could explain both the lack of remnants and the presence of stellar mass black holes we suspect are lurking in the cores. So this eerie quiet in the clusters is not an empty silence. It is a specific, resonant silence that tells us about the nature of the very first stars. Their deaths were not the standard fireworks we see in our modern galaxy. They were cataclysms of a different order, events so powerful they dictated the entire future evolution of their stellar cities, sterilizing them and setting them on a path toward the ancient, quiescent retirement we observe today. The missing supernova are therefore ghosts that shape the present, their absence a permanent imprint of a far more violent youth. The sodium-oxygen anti-correlation is a powerful clue, but it is only the beginning of a much larger chemical story. When astronomers peer deeper into the stellar spectra, they uncover a whole symphony of elemental anomalies, each note revealing a different chapter of nuclear history. Stars within the same cluster show wild variations in aluminum, magnesium, and even the rare element fluorine. These are not random fluctuations. Each specific pattern acts as a forensic tag, pointing directly to the unique nuclear furnace that cooked it. Take aluminum and magnesium. In many second-generation stars, we see aluminum levels skyrocket while magnesium drops. This precise swap is the signature of a specific, high-temperature nuclear process called hot hydrogen burning, which occurs in the deep, searing layers of massive stars. Here, at temperatures exceeding 50 million degrees, protons slam into magnesium nuclei, transforming them into aluminum. So a star rich in aluminum and poor in magnesium is essentially wearing a badge that says, "I was forged from gas blown out of a massive star's interior." Then there is fluorine, an element so fragile it is easily destroyed in stellar interiors. Finding an overabundance of it in some cluster stars was a genuine shock. This fluorine points to a different, more gentle polluter, intermediate mass stars in their final, bloated phase known as the asymptotic giant branch. In the complex dredge-up processes of these dying stars, specific nuclear reactions can actually produce fluorine and then deliver it to the surface where stellar winds carry it away. So a fluorine-rich star tells a tale of pollution from a slower, more evolved kind of giant. Each of these elemental patterns, aluminum versus magnesium, the presence of fluorine, the sodium-oxygen link, is like a distinct fingerprint left at a cosmic crime scene. By collecting them all, astrophysicists are building a detailed profile of the polluters. They can determine not just that the first generation polluted the cluster, but what kinds of stars did the polluting. Were they all rapid, massive supernova progenitors? Or was there a chorus of contributors, including slower evolving intermediate mass stars that released their enriched winds later? The chemical canvas of a globular cluster is not painted with a single brush. It is a layered masterpiece where each abnormal abundance ratio is a stroke applied by a different type of stellar artist, allowing us to reconstruct the entire cast of characters from the cluster's fiery dawn. These intricate chemical signatures are a record of the first stars, but to understand the first moments of everything, we must look beyond the clusters to the cosmos they inhabit. The ancient ages of globular clusters have unexpectedly placed them at the center of a modern cosmological crisis, a profound disagreement known as the Hubble constant tension. The Hubble constant is the number that describes how fast the universe is expanding right now. It is arguably the most important number in cosmology, setting the scale, age, and ultimate fate of everything. Yet, for over a decade, two of our most trusted methods for measuring it have returned stubbornly different answers, creating a rift at the foundation of our understanding. One method looks at the early universe using the detailed snapshot of the cosmic microwave background radiation from the Planck satellite. This relic light from the universe's infancy, when it was only 380,000 years old, allows scientists to extrapolate forward using our standard model of cosmology to predict today's expansion rate. That prediction yields a value of about 67 kilometers per second per megaparsec. The other method measures the late universe directly, using pulsating stars called Cepheids and cataclysmic supernova in nearby galaxies as cosmic mileposts to gauge distances and velocities. This local measurement consistently gives a higher value, around 73 kilometers per second per megaparsec. The difference seems small, but it is far larger than the estimated errors in either method. This is not a minor discrepancy. It is a glaring tension that suggests something might be missing from our standard cosmological model, perhaps a new type of particle or a previously unknown property of dark energy. This is where the ancient, silent clocks of globular clusters enter the debate. They provide a completely independent third way to constrain the problem. The logic is beautifully simple. The universe cannot be younger than the oldest things inside it. By using the most refined stellar evolution models calibrated against the very stars we see, astronomers can determine a robust lower limit for the age of the oldest globular clusters. The current best estimates place that age at around 13.5 billion years, give or take a few hundred million. This is a rock-solid floor. The universe must be older than that. Now connect that age to the Hubble constant. In an expanding universe, the Hubble constant is inversely related to its age. A faster expansion rate means the universe has taken less time to reach its current size. It implies a younger cosmos. A slower expansion rate points to an older universe. The late universe measurement, with its higher Hubble constant, suggests a younger universe about 12.5 billion years old. But that number runs into an immediate and massive problem. It is younger than the oldest globular clusters we observe. A universe younger than its own stars is an impossibility, a logical paradox. The early universe measurement from Planck, with its lower Hubble constant, yields an age of about 13.8 billion years. This comfortably accommodates the ancient clusters, leaving ample time for the first stars to form and for these dense cities to assemble. Therefore, the independent age dating of globular clusters acts as a critical referee. It does not resolve the tension on its own, but it places a powerful constraint. It strongly disfavors cosmological models that require a very young universe to explain a high Hubble constant. Any proposed solution to the tension, whether it involves new physics, systematic errors in measurements, or exotic dark energy, must pass this fundamental test. It must allow for a universe old enough to contain its most ancient stellar inhabitants. In this quiet way, the fossilized star cities orbiting our galaxy are weighing in on one of the biggest debates in modern science. Their silent billions of years of existence ruling out entire branches of cosmic possibility. The shape of a star's life is written in light and color, and nowhere is this more clearly displayed than in the horizontal branch. This distinct stage of stellar evolution appears as a nearly horizontal line on the color magnitude diagrams of globular clusters, a place where older, sun-like stars have exhausted the hydrogen in their cores and now burn helium. It should be a simple, narrow band of similar stars, yet in many clusters this branch is not a line at all, it is a sprawling, enigmatic scatter of points. Stars of the same basic brightness appear in a bewildering array of colors, from cool red to searing blue, stretched across the diagram. This is the mystery of the extended horizontal branch, a visual puzzle that directly maps onto the chemical chaos within the cluster's stars. The key driver is that extra helium we discussed earlier. A star born with a higher abundance of helium in its core has a fundamentally different internal engine. It burns hotter and more efficiently. When such a star reaches the horizontal branch phase, its helium-burning core is more compact and intense, and its outer envelope is thinner. This makes the star appear significantly hotter and bluer than a standard helium-normal star at the same evolutionary stage. In a cluster with only one chemical population, all horizontal branch stars would clump together in one color. But in a cluster with multiple generations, each with different levels of helium enrichment, the horizontal branch fragments. The first generation helium-poor stars settle on the redder end. The second generation helium-rich stars shoot out to the bluer end. And if there's a gradient of helium abundances, you get a full spectrum, a stellar rainbow that traces the precise chemical diversity of the cluster's ancestry. Some clusters even show dramatic gaps in this branch, empty spaces where no stars appear. These gaps are not random, they are thermodynamic deserts, specific combinations of temperature and luminosity where stellar evolution proceeds so rapidly that stars simply do not linger long enough for us to see many of them. They are like missing pages in a book, telling us just as much as the written chapters. So when an astronomer looks at a color magnitude diagram and sees a horizontal branch stretched thin and blue, they are not just seeing stars. They are reading a bar graph of ancient pollution. The precise shape and spread of that branch reveals the mix of helium, the number of distinct generations, and even the relative timing of those star-forming events. It is a cosmic thermometer and a chemical census, all encoded in the silent, burning light of stars that have reached their stable, late life phase. This elegant solution ties the grand mystery of multiple populations directly to the observable architecture of the cluster itself, proving that the past is always written in the present state of the heavens. Our galaxy's ancient clusters are cosmic fossils, but the universe is still building new ones right before our eyes. In the grand tapestry of galaxies, we find star clusters that defy the Milky Way's quiet maturity. They are young, massive, and born from pure chaos. Look at the antennae galaxies, a pair of majestic spirals locked in a slow-motion collision millions of light-years away. Where their swirling arms clash and intertwine, the universe is conducting a spectacular experiment. Within those vast, turbulent clouds of colliding gas, astronomers have identified hundreds of brilliant blue knots of light. Each one is a young, massive cluster, a stellar nursery only a few million years old. These are not the serene, ancient globulars of our halo. They are stellar metropolises under construction, glowing with the fierce light of newborn supergiant stars and echoing with the shockwaves of supernova. Their very existence proves that the recipe for making a globular cluster is not lost to time. It is alive and well, and it requires a specific, violent trigger. A calm, isolated gas cloud will not do it. You need the colossal shock waves and immense pressures generated when two entire galaxies slam together. In these cosmic wreckage fields, giant molecular clouds are compressed to their breaking points, igniting starbursts of such ferocity that they convert billions of solar masses of gas into stars in a single, furious burst. This is the key insight. The young massive clusters in the antennae galaxies and in other merging galaxies like the famous whirlpool are living analogues. They are the present-day equivalents of the violent birth events that must have been commonplace in the early universe. By studying them up close, we get a front-row seat to the process that forged our own ancient globular clusters over 10 billion years ago. We can measure their initial densities, their star formation efficiency, and their early chemical enrichment in real time. We watch as some of these infant clusters, still embedded in their natal gas, are likely disrupted by the very violence that created them, while others, sufficiently massive and dense, will likely survive. They will eject their remaining gas, lose their brightest blue giants to supernova, and over billions of years, dynamically relax into the familiar, dense balls of ancient stars we recognize. So these young clusters are more than just spectacular cosmic fireworks. They are time machines. They allow us to test our theories about cluster formation and survival by observing the entire life cycle, from violent birth to probable long-term stability, all within a single snapshot of the modern universe. They confirm that the ancient relics orbiting our Milky Way were not born in tranquility, but in the fire and fury of an epoch when galaxy collisions were the rule, not the exception. The dense, fire-forged hearts of most clusters are not the only way these ancient cities can exist. Palomar 14 stands as a ghostly counterexample, a cosmic feather drifting in the Milky Way's halo. This cluster is so diffuse, so stretched out, that it barely holds its shape against the pull of the galaxy. If a typical globular cluster is a densely packed metropolis like Manhattan, Palomar 14 is more like a scattered rural village spread across an entire state. Its stars are separated by vast gulfs of space, giving it an exceptionally low density and a large, fluffy physical size. This presents a profound survival puzzle. How has such a loosely bound collection of stars managed to stay together for over 10 billion years without being completely shredded by the galaxy's tidal forces? The very fact that Palomar 14 still exists as a recognizable cluster is a challenge to our models of dynamical evolution. In a dense cluster, frequent gravitational encounters between stars help harden the system, making it more resilient. But in a fluffy cluster like this, such encounters are incredibly rare. It should have dissolved eons ago, its stars scattered into the anonymous halo. Its continued existence forces astronomers to consider two compelling and very different origin stories. The first theory suggests Palomar 14 was never born in the Milky Way at all. Instead, it may have formed within a now-devoured dwarf galaxy that had a very different environment. Perhaps that small galaxy had a much lower density of dark matter, or its gas clouds were more extended and gentle, leading to the formation of this loose stellar association from the start. When the Milky Way cannibalized that dwarf, Palomar 14 was captured as is, a pre-made fluffy cluster that simply inherited a safe, wide orbit. The second theory focuses on that orbit itself. It is possible that Palomar 14 has spent almost its entire existence on a remarkably wide circular path, staying far out in the galactic hinterlands. By avoiding the intense gravitational squeezes that occur during close passages near the galactic center or through the dense disk, it has experienced only weak tidal forces. This gentle treatment over billions of years could have allowed it to retain its original, fluffy structure, like a delicate soap bubble that survives because it never encounters a strong wind. Palomar 14 is more than just an oddball. Its fragile beauty is a critical data point. It demonstrates that the family of globular clusters is far more diverse than we once assumed. Not all are dense, dynamically hardened relics. Some are ancient, tenuous survivors, their very fluffiness a clue to the varied and often gentle conditions that could exist in the satellite galaxies that built our own. The delicate fluffiness of a cluster like Palomar 14 is a cosmic whisper, but the true weight of these ancient cities can shout across the universe. That shout is written in the warping of light itself, a phenomenon known as gravitational lensing. Imagine the fabric of space-time as a vast, taut rubber sheet. Place a massive object on it, like a globular cluster, and the sheet will dimple. Now, imagine a beam of light from a distant star traveling across that sheet. As it passes near the dimple created by the cluster, its path will bend, following the curvature of space-time. This is not science fiction. It is a direct prediction of Einstein's theory of general relativity, and it provides a way to weigh the most massive objects in the cosmos. For a distant galaxy cluster, the effect is dramatic, creating stretched arcs and multiple images of background galaxies. But for a single globular cluster within our own galaxy, the lensing effect is far more subtle. This is microlensing, where the background source is not a galaxy but a single, faint star far behind the cluster. As the cluster moves across our line of sight, its combined gravitational field can briefly magnify and brighten the light from that distant background star. For a moment, the cluster acts as a natural cosmic magnifying glass. Detecting this event within the dense, crowded star field of a globular cluster is an extraordinary technical challenge. You are looking for a specific, temporary brightening of one faint point of light among hundreds of thousands of nearly identical points. It requires precise, long-term monitoring of the same patch of sky, waiting for the perfect alignment. But if astronomers can catch it, the payoff is immense. The duration and shape of the brightening curve tell a precise story. They reveal the mass of the foreground object causing the lensing. Crucially, this mass measurement is kinematic. It does not rely on assumptions about what the stars are made of or their stage of life. It directly measures the total gravitational pull, the true weight of everything in that part of the cluster. The shining stars, the dim white dwarfs, the dark neutron stars, the stellar mass black holes, and potentially that single massive anchor of an intermediate mass black hole. A successful microlensing detection within a cluster's core would therefore be a revolutionary tool. It could finally provide a clean, direct census of the dark population of stellar remnants hiding in the core, the unseen material that dominates the cluster's gravitational dynamics. And if the measured mass is highly concentrated, pointing to a single, heavy object rather than a distributed swarm, it could be the smoking gun evidence for the elusive intermediate mass black hole that has so far escaped all other methods of detection. So, astronomers continue to watch and wait, knowing that within the ancient, silent cities of stars, a chance alignment could, at any moment, focus a beam of light and reveal the true, hidden weight of the cosmos. Each cluster's long story is ultimately a race between two final chapters, a choice between a quiet fade and a violent collapse. On one hand, the relentless pull of the galaxy and the gentle nudges of internal encounters are constantly at work, stealing stars away one by one. This is evaporation, a process that has already begun in clusters like Palomar 5, stretching them into ghostly streams. For most clusters, especially those on wide, gentle orbits, this is their inevitable fate. Over tens of billions of years, they will slowly dissolve, their stars dispersing to join the anonymous population of the galactic halo, leaving no trace behind but a slight enrichment of the galaxy's ancient stellar population. It is a gentle cosmic dispersal, but for the densest, most massive clusters, a different, more dramatic end may await. This is the path of core collapse. As mass segregation continues unabated, the heaviest stellar remnants, the black holes and neutron stars, sink relentlessly toward the center. They form a dense, seething knot of gravity in the very heart of the cluster. In this environment, gravitational interactions become incredibly frequent and violent. These dark remnants can slingshot each other out of the cluster entirely, or they can merge, building up a single, ever-growing black hole at the center. Over an almost unimaginable timescale, this process could potentially lead to the formation of a substantial intermediate mass black hole, the cluster's dark, beating heart. The cluster itself, having lost much of its mass through evaporation and ejections, may eventually be torn apart by the galaxy's tides, but the black hole, a monument of pure gravity, could remain. It would be the cluster's final, silent legacy, a dark anchor adrift in the galactic halo, a tombstone for a city of stars that once blazed with light. The ultimate fate of any given cluster depends on its initial recipe, its mass, its density, and its orbit. The fluffy, diffuse clusters are destined to evaporate into nothingness. The dense, massive giants may leave behind a shadow. In their ends, as in their beginnings, these ancient stellar cities reveal the universe's dual nature, a place of both patient dissipation and violent, lasting consolidation. From ghostly streams to stellar runaways, every mystery we have explored reveals a deeper truth. These ancient star cities are not the simple ornaments we once believed. They are dynamic cosmic engines, complex fossil records, and living laboratories where the fundamental laws of the universe are written in starlight and shadow. Their strange stories have rewritten textbooks, forcing us to see them not as serene relics, but as the key to understanding stellar evolution, galaxy formation, and the very fabric of cosmology. Each discovery, from the impossible age paradox to the hidden chemical fingerprints, from the hunt for intermediate mass black holes to the silent testimony of missing supernova, connects into a single, magnificent narrative. It is the story of how chaos and order intertwine over billions of years, building the galaxy we call home. This journey is far from over. The next generation of observatories stands ready to peer deeper into these ancient cities than ever before. The James Webb Space Telescope will dissect the infrared light from their oldest stars, probing the conditions of the universe's first dawn. The Vera Rubin Observatory will scan the entire sky, mapping the delicate tidal streams and uncovering thousands of new clusters and ultra-compact dwarfs we never knew existed. These powerful new eyes will transform our lingering questions into definitive answers, solving old mysteries and undoubtedly revealing new, even stranger ones. The greatest discoveries about these celestial fossils are still ahead of us. Tell us in the comments which of these 25 strange discoveries captured your imagination the most. Was it the planet orbiting a pulsar, the stars older than the universe, or the silent gamma-ray glow hinting at dark matter? Let us know and subscribe for more deep dives into the greatest puzzles the cosmos has to offer.